Welcome to Signals and Threads, in-depth conversations about every layer of the tech stack from Jane Street. I'm Ron Minsky. All right, it is my pleasure to introduce Will Wilson, who's the co-founder and CEO of Antithesis, someone who started out studying math and then somehow found himself working on distributed databases and now running a startup that is trying to change how we all do testing, hopefully for the better. Jane Street is actually both a customer of Antithesis and an investor, something I want to talk about a little bit farther in. But thanks for joining me.
Yeah, hopefully for the better, but I think it would be hard to make it a whole lot worse.
Oof, fair. So let's just talk a little bit about kind of how you got here. You started off studying mathematics. You've done a bunch of other things. You're now doing a lot of what seems to me is really hardcore systems work. Tell us a little more about that journey.
Sure. So when I got to college, it was the time when everybody was super, super excited about computer science. Like Facebook was new, Google was new, everybody was going off and joining those companies and, making a lot of money and doing really cool stuff. And, I basically made a very large mistake, which was I got to college and I was like, wow, that computer science stuff seems really cool. Too bad it's over. Right. Too bad. Too bad. All the interesting problems have been solved already. Like, look, somebody's already made Google. Like, what else could there be to do? So I basically ran kind of in the opposite direction. I knew a little bit about how to program. I taught myself when I was a kid, but I basically avoided studying computer science at all and ran into like the most abstruse forms of mathematics, which just seemed, more intellectually interesting, and also like nobody was going to run out of math anytime soon.
That's true. Although this whole thing of like maybe AIs will run us out of math, but that's like a
if I were
making a problem.
If I were making that decision again today, I might have picked something different that AI is not so good at.
So when you say like abstruse mathematics, like what kind of stuff were you interested in?
I did a bunch of different things. I liked a lot something called representation theory, which is something very useful in mathematical physics. It's basically the study of like homomorphisms from general abstract groups into vector spaces, either finite or infinite dimensional. It's pretty neat. That was actually a little bit too useful. That was a little bit too applied. So I also, I also got into some like mathematical.
There are like actual matrices there.
Right. Well, there's actual matrices, and you can actually use this to like, do particle physics, which, I don't know. So I also did a little bit of set theory. I got into something called large cardinal theory, which is so abstract it almost sounds like a parody, right? It's basically what new forms of mathematics can we develop if we add assumptions that certain very large infinite numbers exist? And the Wikipedia pages on this stuff are a total hoot if you want to look at it.
I have sadly looked more than a little bit at large cardinal theory, and it is fun and wild and indeed not the most practical of all.
This is the only podcast I can imagine where the host might say that as a response.
All right. So you had like a promising start of a career in mathematics. Why did that not go anywhere?
Oh, well, I got to my senior year and I did actually apply to grad school, and I actually got into grad school a few different places, and I was all set to go off and do my PhD in math. And then I just looked around and I looked at my fellow classmates who were going to grad school, and I looked at my professors, and I looked at myself, and I had a very important moment of self-realization, which was that I am never going to be a world-class mathematician. Because basically for the same reason that I'm never going to dunk, right? I'm never going to be a world-class basketball player. There's a certain measure of natural talent and random variation that is just required. And like, yes, you can definitely get better at basketball or better at math by working very, very hard. But these are both professions with this like incredibly skewed return distribution, where if you're not in the top 0.00001% of people, you're just never actually going to have a great time. And so, I realized that I could spend 6 years in grad school or longer and, eventually get some job, teaching somewhere as an adjunct or something. And, or I could not do that. And I could sort of bail out of this process sooner. And I realized that was what I had to do.
Got it. And then you transitioned into what? What did you do from there?
Well, I actually initially was off doing a little bit of biomedical research. I had interned when I was in college and actually before college at a small biotech startup. And I'd done a bit of that, and after that I bopped around in a few different sort of dead-endish jobs. And it was at one of those that I had this crucial realization. And the crucial realization was that actually my ability to write a janky Python script was unbelievably economically valuable, right? Like I was sitting at my job and, my boss had assigned me some like enormous pile of drudgery. And, I looked at it and I wrote a Python script and it took me 45 minutes and it automated the enormous pile of drudgery. And I was like, okay, here, I'm done. And he looked at me with this like expression of dread and was like, that was supposed to be your work for the next 3 months. Like, and that made me something in my head. I was like, interesting. Maybe I should get better at this programming thing. That seems like it could be good. So, I went and I taught myself how to code for real, and I, did some online classes, and then I eventually got my way into a number of tech startups.
So how do you actually learn how to program? My overall sense of the world is that the world is actually very bad at teaching people how to program. Universities, I feel like, are especially bad at it. They do this weird form of performance art where professors hand out assignments and then students fill in and resolve it, and then it's given back and looked at once, and then it vanishes like a puff of smoke. It's like the evanescence is part of the art of it all. And real software is nothing like that, right? It's a thing where the kind of permanent evolving state of the software is like part of what's important about it, part of what you need to like optimize for when you're writing software are these, not like just the functional properties of what the software does, but the non-functional properties around how extensible is it and how easy will it be for people in the future to understand, and what kind of performance problems are you creating in the future, and all these things that like don't show up in the kind of very small scale fake environments where you learn how to code. And you need to do very different things to learn to be good at it. And what do you do?
Yeah, no, that is super, super true. And so I did actually try to solve that problem a little bit, but I will also qualify my answer by saying that my main goal was to get hired at a software company, not to become a great engineer yet.
Fair.
I think I knew somewhere in the back of my head that becoming a great engineer would require working with other great engineers and, being mentored by them, as indeed it did. But basically what I did was I followed 2 tracks, and I was on paternity leave at the time, which made it easier because I could sort of do this nights and weekends and basically I studied a lot of academic knowledge, right? All the stuff that I had missed in college. I went and learned about complexity theory, and I learned about the theory of algorithms, and I learned what a data structure is, and like all the stuff that everybody else learns their sophomore year. So I sort of, I jammed all that into my head, using a bunch of YouTube videos and, online resources and so on, which there's a lot of these days. And then I also just tried building things, and I mostly focused on things that were interesting to me and things that were hard. And I tried to pick a pretty broad set of things that would force me to learn different skills. So, I wrote my own little ray tracer, and it was like a
classic,
pretty crappy ray tracer, but like I did learn C++, and I did learn a lot about, how to do object-oriented programming and how to do memory management and so on in the course of that. And then I wrote a little toy compiler, and I wrote a little computer game, and I wrote like a bunch of different I wrote a little graph database. I did this
prescient. That was
Yeah, that's right. Turns out that those were actually a fad. They never really took off.
Sure. Graph databases has not really taken off, but there's a lot of database theory.
There's a lot of database theory. That's right. And that actually was part of what got me interested in databases and what eventually led me to working at FoundationDB, which is where I did find really great engineers who were able to mentor me and who made me actually somewhat competent.
Got it. And then somehow from the work at FoundationDB, you ended up eventually founding Antithesis.
Mm-hmm.
So tell us about that.
Yeah, so FoundationDB was a magical place. It was, I think in some ways a little bit like Jane Street, right? Like it's just one of these places that you walk into and everybody is brilliant and everybody is incredibly humble and everybody is incredibly nice and good at their jobs, and it just hums with this extraordinary energy. And one of the brilliant things that had happened at FoundationDB, it's a thing that should happen in more software projects, I think. They sat down and were like, we're going to build a new kind of database. This is a kind of database which at the time people believed was literally physically impossible to build because of a misunderstanding of something called the CAP theorem. And we can get into that more if you want. But basically they were like, okay, we're going to try and build this new kind of database. What do we need to have in order to build this database? And they realized that in order to build such a system, you would be totally foolish to do it without a powerful deterministic simulation framework that could sort of test the database in every possible configuration, in every possible mode of operation, in all possible network conditions and failure conditions and so on, with any amount of concurrent user activity, and have that all be replayable deterministically. And if you think about it for a second, it's like, yeah, you would be foolish to build a database without that. But, they were the only people I knew of who had actually acted on that insight. And so they built this extraordinary system.
And pause for a second and say, what is a deterministic simulation framework?
Right.
Right. There's a few words there, deterministic, simulation. I feel like understanding how those play out is maybe useful.
Right. Sure. So basically, let's start by talking about property-based testing in general, in the abstract. Quick check, right, from Haskell, or I think OCaml has its own property-based testing system, right?
Every functional programming language has at least 3 of them.
Right. And then in Python, you've got Hypothesis. So property-based testing, the basic idea of it is I have some piece of code. Rather than sit there and write a bunch of unit tests that do particular things that I've thought of ahead of time that take particular actions, I'm going to just tell my testing framework what you can do to my code, what actions you can take, right? If it's a little data structure, it's maybe I can insert an item and I can pop an item and I can query for some item or something. And then you set up a bunch of randomized generators which do all these things in random orders. And then you figure out what the invariants of your program are, right? Probably an easy one is it shouldn't crash. But maybe a more interesting one for a data structure is if I insert 5 things, then there's 5 things in it. But actually, that's not a great one, right? There's a higher order one, which is if I insert n things and don't remove anything, there's n things there. But then we can make that even more abstract and be if I insert n things and then remove m things, so long as n is bigger than m, I'll have n minus m things in there, right? And so you can sort of get quite clever with these things. And then the magic is you now have not a test. You have a thing that will produce an infinite number of tests, so long as you keep running it. And it will basically try your thing in many, many more permutations and combinations than you would ever have thought of. That's the basic idea of property-based testing, right?
That's right. And these classic frameworks like QuickCheck in some sense automate the hardest part of this is generating a good probability distribution. Mm-hmm. And you were framing this in terms of operations where you have sequences of operations on some kind of system. And that's already leaning a little more systems-y. I feel like the classic functional programming version is more I'm going to test my map data structure, right, or whatever. And then often what you're putting in is just, lists and whatever shapes of containers, whatever that you want to use for doing straightforward things. And often you're thinking about it less in terms of sequences of operations and just some fairly broad shape of data that you might want to put in, and you want nice ways of generating good probability distributions. The question of what counts as a good probability distribution is actually quite a complicated one.
It is very complicated.
And so in some sense, there's 2 things you need to specify. There's the properties that are supposed to be true and the probability distributions for generating examples. And that's kind of the whole bulk.
Right. And so then one of the rules of all human endeavors is that every good idea is rediscovered 17 different times by different people who are in slightly different subdomains. And so they didn't talk to each other. And then they create their own language and set of concepts for it. And that's all very confusing. Yep. And this is also true of property-based testing, which has been reinvented tons of times. And one of the most common one of the most well-known other times it was invented, it was called fuzzing, which is a very, very similar thing conceptually, right? Fuzzing is more from the security world, but if you squint, it's the same thing. I have a property, which is my program shouldn't crash, shouldn't have memory corruption, shouldn't have security vulnerabilities. And then I'm going to feed in a distribution, and the distribution happens to look like stuff to parse, maybe that has errors in it or has maliciously crafted content. And I'm going to have a random generator, which is my fuzzer, which is going to keep sending in stuff until I find a failure of the property that I care about. And this is a totally separate group of people who solved many very similar problems in some different ways and in some similar ways. And the 2 sides just never talk.
That's right. And the early versions of fuzzing were very simple on the probability distribution side. It's just white noise basically for throwing into things. For some of the very early research and just take the Unix utilities and throw white noise at them and see what happens.
Yep.
And the language of properties was incredibly impoverished. It was like not much better than doesn't crash.
Yep, but the fuzzing people had a clever trick, which the property-based testing people did not have. The fuzzing people realized that you don't need to make this a black box process. You can actually track things like code coverage, and you can see what your inputs make your code do. And then you can use like a genetic algorithm or an evolutionary algorithm to adapt your input distribution as you go to find more and more interesting behaviors.
That's right. You basically like have these tentacles into the program and you feel out where you are in the state space and try and explore more of the state space of which branches you've gone through and all of that. Right. Yeah. It's definitely like an extra idea. And like, you know, a bunch of the property-based stuff came out of the functional programming world, which has this, we're going to derive probability distributions from types. Totally makes sense from that. And this like, no, we're going to modify the compiler and we're going to like do a bunch of weird ad hoc stuff to like try and explore the state space. It's a very different but very good idea.
Yeah, well, the interesting thing is like you are trying to solve the Turing halting problem here, right? We know you cannot do it. We know that there's no one technique that's going to find all the bugs. And so I actually believe that the correct response to that is just to like throw everything at the wall and see what sticks. Like you should try and have very clever probability distributions, and you should try to have, you know, evolutionary algorithms, and you should have, you know, constraints and, you know, constraint solvers, and like, I mean, you like do everything you can, add some ML, like whatever. Like we're up against a very hard problem. And the nice thing about a basket of tools is that if you're careful about how you architect them, no tool can like make the situation that much worse, but there are certain situations where it can make it much better. And so by having a broad distribution of techniques, you're likely to have something that works on a larger space of programs.
Right. Particularly because we're doing testing, right? It's just like you do an extra thing, it takes some time.
That's right.
But it doesn't break anything. It's just like if it was the worst thing it can do is not find any bugs for you.
That's right. And you have to be a little bit more careful about that once you have like sophisticated evolutionary tactics, right? Because it could be that some technique you use like pollutes your distribution in some way that makes it harder to find other bugs. Sure. But, you know, that just means you have to not be totally naive.
Got it.
Yeah. So, okay. So there's all these people doing randomized testing. And what's interesting is nobody until very recently had ever applied any technique like this to what I would call real software. Like, and this is like not a knock on Haskell or, you know, or small functional data structures, certainly not a knock on parsers written in C and C++. What I mean by that is like nobody fuzzed or used property-based testing on a database or on a computer game or on a large distributed system or on an operating system or a kernel. Like people have lately started to do these things, but by and large, it was not happening until quite recently.
I feel like it wasn't common, but is it really that it wasn't done at all? Like I've talked to like John Hughes about stuff that the Quick Check folk did, where they like, you know, worked with like auto manufacturers for fuzzing their like, you know, super weird network inside of the computer and things like that. So I feel like there is stuff that like I think should qualify as real software that's more than like the traditional like toys to which this stuff is applied.
Right.
There's at least been some commercial applications.
I think people did some of it, but I would say it was vanishingly rare. I mean, all of these techniques maybe arguably are like vanishingly rare, like to a first order approximation, like 0% of people use them.
Sure.
But I think it was especially uncommon to try and use it on big stuff.
Yeah, I mean, I think it's felt relatively niche. I think there are things that qualify as more serious applications of it, but like much rarer than they deserve to be applied.
And basically, I think that this is actually for somewhat good reason. So when you have big software, big complicated software, you sort of have, and I promise I'm getting back to your original question, which is what is deterministic simulation testing? Basically, when you have big complicated software, there's two things that get dramatically harder. The first thing is the state space of the software that you are trying to explore is really complicated. And it is probably complicated in such a way that the fuzzing trick of just, you know, recording code coverage is no longer a very good map for where you have gotten in the software, right? Consider something like a Python interpreter. If you hit 100% code coverage in that, you have not gotten anywhere close to exhausting its behavior. Or consider something like...
And that one is just because like the state space is much bigger than just like where you are in each branch of the code. Like your code
Right.
location doesn't tell you that much about the state space. There's like lots of other things going on that
Right,
are
like
really important.
what's in various variables, like what's in memory, like
Yeah.
all this other stuff. And if you try and like take the Cartesian product of that with all the coverage, it's like way too big and you're not going to make any progress. Or consider a distributed system, right? Where just what coverage you have gotten might be less important than like what order you have encountered coverage across different nodes in some distributed algorithm. And so basically, knowing where you are and fully exploring the program becomes harder, both from the fuzzing philosophy of we're going to use signals like coverage to determine where we are. And it also gets harder from the like PBT philosophy of we're going to have really clever, intelligent random distributions, because basically you have to just get lucky so many times in a row to get something useful happening that you just kind of, it's intractable to solve the problem purely that way.
Right. You more or less probably can't do it fully obliviously, right?
That's right.
The oblivious thing where you have the distribution chosen ahead of time and you're just throwing things at the system, like you kind of have to be responsive to the state of the system if you're going to get the right kind of coverage. Although it's worth saying, like when you say covering, like you never actually cover the state space, right? The thing that you're doing is always weirder and more heuristic because the actual state space is like highly exponential.
Yes.
And so you will not, in any reasonable testing budget, be able to test any appreciable fraction of it. So there's some weird question of like taste, of like which vanishingly small subset of the scenarios is it important for you to cover?
Yes, totally true. And we will come back to that. That is like, that's like, right, you want to cover all of the interesting parts of the state space and you want to try and do it as quickly as you can. And that is a whole nother dimension along which this is hard. Okay, so then there's a second problem with these larger systems, more quote unquote real systems, which is that they don't really look like the kinds of systems that people have traditionally applied fuzzing and property-based testing to in two kind of ways. One is that they tend to be interactive, right? They tend to not be things that accept an input and then do a bunch of computation and then crash or don't, right? Which is kind of what fuzzing is optimized for, right? They tend to be things that take a little bit of input and then send you a response, then get a little more input and then do something. Like imagine a web server or a computer game. It's like got this interactive flow to it, which makes the whole fuzzing model of like, I'm going to come up with what is a good input to break the system and send it in and see what happens a little bit more complicated. Then the second thing, which makes the state space exploration problem even harder, is that these systems are all non-deterministic. And this is in some ways, I think, the crux of it. Because basically, computers are machines, right? They're like real physical machines in the real world. And in order to make those machines really efficient, CPU designers have done all kinds of evil and awful things to make them, that have this side effect of making them non-deterministic. Meaning that if you try and perform the same computation on the same computer twice with all the same inputs, once you have things like threads involved, once you have things like timers, once you have things that need to interact in any way with the real world, with network sockets, with hard drives, suddenly your computer program is not a pure function, right? Unless you have written it in Haskell and have been very, very careful. It's a big, complicated, weird state machine with all kinds of co-effects from the environment that can mean does something totally different each time you run it.
Yep.
Okay.
Although one of the weird paradoxes of this is, it is often the case that the individual components are actually all very close to deterministic. It's just that they wildly depend on initial conditions, and their behavior is kind of chaotic and diverges from predictable things. So it's like, actually the thread scheduler is a completely deterministic program in some sense, right? Except, and the timers like work largely deterministically, but like your memory, it doesn't always have the same latency. There's like a cycle where the memory gets refreshed and it'll block out for a very little piece of time. And, did you start your program at exactly the same time in the memory refresh cycle, the two times that you ran it? Like probably not. And then like all of these things compound and multiply as you have multiple systems talking to each other, and like the small differences become big differences, and effectively this non-determinism kind of gets like pulled almost out of nothing.
Yeah, that is a fantastically accurate intuition. And we haven't started talking about our technology yet, but like we're able to measure that intuition. Like we can empirically tell you what the Lyapunov exponent of your software is and like what its chaotic doubling time is. And it turns out that for Linux, it's insanely fast. Like basically, if you change 1 bit in the memory of a Linux computer, the whole state of the system is completely different, like within tens of microseconds. It's actually crazy.
That's shocking.
Yeah, it's nuts. I did not believe it, but it's true.
Yeah, I'm still not sure I do, but
I can show you. I can show you. Okay. Anyway, so why is this non-determinism so bad? So it's bad for 2 reasons. The more obvious reason is it means that if I do my cool fuzzing property-based testing thing, I run some fantastically expensive computational search, I find the bug that's going to ruin my life, and then, if I don't have exactly the right logging in place, if I can't just look at the source code and one-shot the bug, I may never make it happen again. And that is very, very frustrating. Now my testing system has just made me feel bad, right? It has, it's just, that's not
something is wrong.
That's right.
Good luck.
You'll never know what it is until you find out at 3 a.m. when your pager goes off. So that sucks. And then there's a second problem with it, which is that it makes the fuzzing trick of look at what inputs have made me do useful things so far, and then try small modifications on those inputs, break down and become much less performant. Because if putting the same input into the system again might not get me to the same point in the state space, then putting a slightly tweaked one is extra maybe not going to get me to the same point in the state space. And so this like optimization loop that all of fuzzing kind of implicitly depends on doesn't work very well.
You basically need the fact that there's like a kind of random input, like more or less your random number generator, and like a function from that into the behavior, and you really want that function to be a real function.
That's right.
Which you can always run and get the same answer so that you can actually explore that space. Where if like every time you try it, there's just like a new version of the function that like is spiritually similar, but like has all different behavior.
It makes fuzzing degrade into random guessing. That's right.
Yeah.
That's
okay.
Right. So that brings me back to what is deterministic simulation testing? And the idea here is the somewhat crazy one of like, we can sidestep all these issues if we just make all of the software deterministic, which sounds a little bit insane and maybe like a little bit useless. Like it's like, assume you had a can opener. How do you make your software deterministic? And that's a very fair criticism up until the existence of Antithesis, which I will get to later, has kind of solved this problem for people. But in the absence of that, what we did at FoundationDB was we wrote our software in such a way that it could be run completely deterministically. So we could simulate an entire interacting network of database processes within one physical Linux process with deterministic task scheduling and execution, with fake concurrency, with mocked implementations of communication with networks and with disks, right? We could cause database processes to have simulated failures and restart. We had to do all this with no dependencies whatsoever, right? Because as soon as you add a dependency on Zookeeper or, Kafka or some other program, like you lose this ability to run in this totally deterministic mode. But it made us so much more productive to be able to test our software this way that it was worth it to us to not have any dependencies.
So is it fair to say that the key enabling technology here is dependency injection? Like you have a bunch of APIs that let you interact with the world. Like most of what you write in a usual program are in fact deterministic components. Like, you do some computation, the result is deterministic, but there are some things that you do that aren't. Like you ask what time it is. Mm-hmm. It's like, well, now you're really 2 different pieces of hardware, right? There's like a clock and a CPU and they're interacting, and like, who knows what's going to happen when you ask what time it is. You send or receive a network packet, you ask for something from disk. So the thing you can do is you can just like enumerate all of the APIs that you have that introduce non-determinism and just have them have 2 modes. There's like the regular production mode where it hits the real world and is non-deterministic. And then there's test mode where you just have control, and you can, behind all of those calls, you can have a simulation that gives sort of the response to the API where you have control over it, and you can thereby force it to be deterministic. Is that like the basic trick?
Right. Well, that's the basic trick, but you're left with one really, really, really big problem, which is concurrency. Like if your program, even if your program only runs on one computer, you probably have threads, and then the OS is going to schedule them in like God knows what order. And, they also, by the way, will take non-deterministic amounts of time to execute actions. Thank you, Intel. And thank you everything else running on your computer, right?
Well, I mean, thank you, Intel, because if they didn't do that, things would be way slower.
Super true. So that's people can solve that, right? Like there are languages with sort of cooperative multitasking models of concurrent programming, which you can actually plug in a deterministic scheduler and make that all work.
Yep.
But then if you have multiple processes running on different computers, now you're really in trouble, right? Now, how long did it take that network packet to get from this computer to that other one is something that's completely outside of your control. And if you want to try and run them all on the same computer, you need to create some way of faking processes on different computers running on the same computer in some sort of cooperative multitasking runtime so that you can make it all deterministic. And there are people who've done that. We did it at FoundationDB. I think you guys did it at Jane Street.
That's right. Yeah. One of the reasons I sort of know the bag of tricks is that this is more or less exactly what we have done and hit the exact kind of same set of issues and the same basic commitment to we will write all the code ourselves. We had kind of weirdly fallen into by using an obscure programming language. Mm-hmm. So we had this whole OCaml ecosystem where we had really deep control over the whole thing. And so a lot of our systems, not all of our systems, but a bunch of our systems are built in this way where we have this kind of end-to-end control and can do this kind of deterministic simulation. And it's absolutely critical for all the reasons you said. It really helps you go faster in many different ways.
Yeah. I think something I haven't said yet is this all sounds like a lot of work, and it is a lot of work, but it was so game-changing at FoundationDB. That company could not have existed without this technology. We built a thing that everybody thought was impossible with a team of 10 people, and we did it really, really fast. And we did crazy things that nobody would ever dare to do without a testing system like this. I mean, I'll give you 2 examples. One was we deleted all of our dependencies, right? And in particular, we deleted Apache Zookeeper, which we had been using as our implementation of consensus, of Paxos. And nobody writes their own Paxos implementation. That's like a thing that insane people do who want to have bugs. And we did it, and our new one was less buggy than the officially good one from Zookeeper that everybody uses. Later we basically deleted and completely rewrote from scratch our core database concurrency control and conflict checking algorithm to make it more parallelizable and more scalable and faster, which again is just a totally crazy thing to do. I don't know of other databases that once they have gotten that piece working have rewritten it, let alone rewritten it to make it more theoretically scalable and cleaner. That's just nuts. But if you have a system that can find all the bugs really, really fast, it frees you to just do crazy stuff like that.
Okay, so this seems like a great idea. We think it's a great idea, which is why we've done it. FoundationDB thought it was a great idea. It's also totally impractical.
Totally impractical.
Right? Because the whole thing of we'll just do everything from scratch. It's okay, yeah, maybe a database system should do that. And maybe some crazy trading company that made a decision 20 years ago to use a weird tech stack can do that for all sorts of reasons. But it's not a generalizable tool.
Right.
And Antithesis is trying to be a company that sells a generalizable tool. So how do you go from the good idea that's totally impractical to a thing people can use?
Right. So basically we've talked about how there's sort of 2 key obstacles to making a really, really powerful randomized testing system, what we call an autonomous testing system that can find all your bugs really, really fast. One is need to actually explore the state space extremely quickly and find all the bugs. And the other is this determinism issue, which both impacts the usefulness of finding those bugs and also makes it just harder to explore the state space. And basically what we're trying to do is the absolutely insane hubristic goal of solving both those problems in full generality for every piece of software in existence. And so basically the important thing is we solve them in the reverse order. So once you solve determinism, that actually gives you a huge leg up in efficient state space exploration for all the reasons we've already talked about. Mm-hmm. And I can go into more detail about how we use that. Okay, so how do we solve determinism? That sounds kind of hard because, as we've just talked about, all kinds of things that you want to do on a computer are non-deterministic. So there's other people who have tried to do this. There's people who use frameworks, right? Like the one that you guys have at Jane Street, or like the one that we built at FoundationDB. There's since been a bunch of open source ones built for various programming languages and runtimes. That's cool. It only helps people who are committed to using that framework, willing to write all of their software with that framework, not use any dependency it's not in that framework. It's not general, right?
Yep.
Not a general solution. Can't do it that way. There are people who have tried to solve this problem with record and replay, where basically, like, as I'm running my program, I write down the result of every single system call in the exact moment at which it was delivered. And then if I want to run my program again, I can just replay all of that without actually talking to the system. And that works pretty well for a thing running on a single node. Doesn't work very well for distributed systems. It's also just not very scalable.
Although there's a critical idea that you snuck in there, which is where you said the word syscall, right? So the whole, like, the kind of FoundationDB/Jane Street/ whatever version of doing this at the library level is like there are particular function calls inside of a language that you're going to make swappable. But here what you're doing is saying, actually we're going to do this at the OS level.
Yes.
Right? At the bottom, actually all the non-determinism generally comes in from the operating system and from concurrency. And concurrency is somewhat mediated by the operating system. So system calls are anyway one huge source of non-determinism. And so the idea of these kind of, record replay things are, we're just going to do the dependency injection at that level. And we've already now stepped up a big level in generality, right? I no longer have to own your programming language.
Right. It's gotten better.
It's gotten better. It's a big step.
We're not there yet, though.
Okay.
So we're not there yet for two reasons. One is it's still not fully general, right? This is only going to work for the operating systems that you've designed this to support. And maybe that's okay. Maybe you think it's fine because everybody uses Linux. But like
weirdly, seem to be true now.
People write iOS apps, man. Like people write computer games. They mostly run on Windows. There's other OSs out there. But I think, also doesn't work great for distributed systems, although you can kind of hack it, and there's a few people who have.
Actually, why doesn't it work great for distributed systems? The syscall layer gets you a hook into all the distributed, all the distributed communication comes again through the OS.
Yes.
So why can't this generalize to that?
Basically, all of the record replay systems out there are designed to do this for one process.
Got it. So it's not so much a fundamental question as an engineering question.
Correct. It's just like the UX is not very good.
Sure.
But I think the more fundamental limitation of these things is the scalability problem, right? Like it is just a vast amount of data to write down every single syscall that your thing ever did. You're already doing a computationally expensive search. You really don't want to hugely increase the overhead of that. And it doesn't actually get you true determinism.
It lets you replay a non-deterministic run.
Correct.
But it doesn't let you play it doesn't let you play things out in a deterministic way. Because every time you do a thing you haven't previously captured.
Correct.
You just got to do it.
Exactly.
Right?
Exactly.
So it's like it's a weird halfway house, right?
Exactly. So basically what we decided to do was just go another step beyond that and say, okay, we're going to do the dependency injection, as you put it, at an even lower level. Let's just get under the operating system and let's implement a deterministic computer, which is a thing that you can do these days without creating custom silicon because people have virtual machines. Hooray. So basically, we just have to write a hypervisor that emulates a fully deterministic machine, and then we don't have to touch your OS at all. We don't have to touch anything you do at all. You can just run your stuff unmodified.
Right. And so your crazy hard thing to do is possible because people did a super weird, crazy hard thing to do years ago. And this was part of the historical failure of the operating system, where it's we're going to use the operating system back in the 60s or 70s, where it's good. We have these multi-user operating systems. We're going to have ways of isolating different people's programs from each other and stuff. And then some number of years, we're going to be oh yeah, none of this works actually. Unix is very badly designed. It doesn't solve any of these problems. So instead, we're going to have a new abstraction where we are going to simulate things at the level of machines. The hypervisor is basically the computer that whose upward interface it exposes is a fake machine and lets you run different virtual machines on that hypervisor. And then once you have the hypervisor, in some sense, the path is clear, right? That's the layer at which, in some sense, before we said, all the non-determinism comes from the operating system.
But no, it comes from the CPU.
It comes from the
it comes from the hardware.
It comes from the
timers, right? It comes from
all the different pieces of hardware introducing that.
So
you just got to be that's the layer at which the non-determinism comes, and that's the layer at which we can instead do a deterministic simulation of what a machine is.
Correct. And our hypervisor is a little bit more ambitious than just being a deterministic hypervisor, which was already kind of hard. But in order to make this really work well, it also needs to be really fast, right? Close to native speed, or even in some weird cases, a little faster than native speed for most code, which is an interesting thing that we've pulled off. But then there's another property that's also really important, which is we are trying to do this huge branching exploration through the state space of a computer system. And so if we're running down multiple branches on the same physical host that is running the hypervisor, it's really annoying if we have to like store a separate copy of the memory for each of the guest operating systems that's running inside of it. That would be a lot of RAM, right? Mm-hmm. And so what we do instead is we deduplicate memory pages at the host level using copy on write. Nice. So that if, one of the guests is doing something and it doesn't affect some particular page in memory, it just inherits a copy of that from its ancestor. And, sibling VMs can just be addressing the same underlying memory on the host system, which means that we can do this with massive concurrency on very big computers and, explore really fast.
Got it. Okay. So this kind of like brings into focus, like what is the thing that Antithesis is providing in the end, right? It's trying to give like all of the upsides you described of having this very powerful testing system that can efficiently explore lots of different behavior. Mm-hmm. But it does it in a way where the amount of work that you have to do to use the system is very low.
That's right.
It's like, what is your API to Antithesis? It's actually what you're doing already. Like you threw a bunch of stuff in a Docker container before, you throw a bunch of stuff in a Docker container now, you're just like running a VM somewhere. It's like, yeah, you just run a VM somewhere else. You run a VM on Antithesis's servers, and then they get to like use all of this fancy tech to make it efficient and be able to do all this exploration. And like, you don't have to do anything clever to make your system testable.
That's right.
It's just like,
we magically find all the bugs and they're magically reproducible. That's right. It's very straightforward. And, and the key there, right? I said we magically find all the bugs. That's the second really hard thing I mentioned, right? Once you've made the system deterministic, you still need to find all the bugs, right? You still need to do this state space exploration. And you now need to do it because you've enabled exploration of way more complicated computer programmers than parsers, and little data structures written in Haskell and so on. You now need really, really smart state space exploration. But because we have determinism, we can be smart about it. It doesn't degrade to random search. And so we've also got, a whole large chunk of our company that is like doing fundamental research on how to like do this data exploration faster and more efficiently for wider and wider classes of programs.
So to jump back for a second to like the initial framing of like, this is all kind of comes out of like property-based testing, mm-hmm. in a sense. We spent an enormous amount of time talking about one half of property-based testing, which is essentially the random generation of the generation essentially of the probability distributions, right? How you explore the space, and a bunch on the mechanics of how you run it, but very little on the properties, mm-hmm. right? And like, if you want to find all the bugs, right, you have to know what the program's supposed to do in the first place.
Yes.
So like, how do properties fit into this story?
Right. So this is actually a little bit easier than people think it is. And I believe that, like, I think a lot of the problem here actually is that property-based testing was invented by like mathematicians and functional programming people who were thinking of it in the same area as like formal methods and stuff like that. My colleague David McKeever calls this the original sin of property-based testing, is that like people were coming from this very, very mathematical background. And so they were thinking of it as like, you have to exhaustively enumerate all of the properties of your system. And my belief is that you don't actually have to do that. And the reason why I don't think you have to do that is that computers and computer programs are very chaotic, and they are very good at escalating any misbehavior of your program into much more obvious and extravagant misbehavior. And so you can actually catch a very, very large number of bugs with a partially specified system. So to give you a concrete example of this, right? Like if I have some memory corruption in my C++ program, and I don't have ASAN enabled, so I'm not going to find the memory corruption directly, that could still manifest in a lot of ways. It could manifest as my program giving wrong answers. It could manifest as like weird garbage or glitches, in some response I get. It could manifest as a crash. It could manifest as an infinite loop. It could manifest as like corruption of some other random invariant in my program somewhere. And so if I have a property that's set up to catch any of those things, there's like a decent chance that when I shake the box enough, I will be able to detect that bug, even though I haven't thoroughly specified every aspect of its behavior. And that same idea actually is true for much broader classes of bug than memory corruption.
So I think what you're saying is like true for a part of the space, but I don't think you're going to get all the bugs that way, right? I think there are lots of areas, and I think we as computer scientists and really as software engineers rely on this kind of brittleness property all over the place, right? Where like, the fact that you can like find the bugs that you can.
It's actually kind of why normal non-randomized testing works so well, I think.
That's right. But I also think whether it works depends on the kind of things you're doing and the way that the code is structured in important ways. Like the most obvious exception to this is numerical bugs, where like numerical bugs just don't show up this way. Like you get the calculation a little bit wrong, and then like, your curve doesn't go up and to the right quite at the speed that you want it to. But it's often very hard to get any kind of bright line demonstration that you've done something wrong and know where you've done something wrong.
That's right.
I think there are other properties too. I mean, from our kind, if you're building a trading system, and like the trading system might operate perfectly well and it never like breaks, but like it's just like more aggressive than it should be. It sends larger orders more often or less often or not placed quite properly in the book. And I think if you don't do a good job of specifying the properties, I think those kind of systems are very hard to test. And this kind of coarse-grained, well, let's kind of look for like gross misbehavior and shake the box a lot, is just like not going to get those things at all.
Yeah, so totally agree with you. What I've said so far only covers a subset of the bugs. I think that there are a lot of other ways to add and refine properties incrementally. Like the key, like I am interested in how to do this absolutely perfectly because I'm a testing fanatic, but I'm also like a pragmatic business owner, right? So I want to give customers like an easy way on, which is just, add the most basic possible properties that all software should have. And then I want to give them a nice, gentle ramp towards more advanced usage. And I think what the nice, gentle ramp looks like for most people who are not sophisticated property-based testing experts is actually, others have already done it for us. I think it looks like observability and alerting. Like if you think about a system like CloudWatch or a system like Datadog or whatever, they have already built, in some sense, like the second half of a property-based testing system, right? You can specify what you don't want to see. And then you can define alerts on those things. Hey, memory of this thing should never exceed this number. Oh my gosh, if you ever see this log message, I want to be alerted right away. Those are all properties. Like they're not very good properties, but they're properties. And I think the main reason they're inadequate is that with something like CloudWatch or something like Datadog, you only find out that those properties have been violated when your customers do. Right? If you could move that experience, that UX into the testing world, into before you deploy, I think it's actually an amazing sort of interactive way of defining and then refining your system's properties. And I think it's a thing that's like actually quite accessible and intuitive to quote unquote normal developers.
I see why you say that, but I worry actually that observability style approaches will scale very poorly. Because part of what, as I understand it, the antithesis approach relies on is the ability to take the work you're doing, the testing work you're doing, and run it at kind of massive, like incomprehensible scale. And I think observability rules tend to rely on the fact that, you see the things as often as they happen in real life. And so you can get away with like soft properties that aren't quite the properties that you care about, but are like indicators of and predictors of the things that you care about. So there's, you sort of get to specify things to flag you. And the key thing is to make them not flag you incorrectly too often. But I feel like something like Antithesis depends pretty critically on the violations being real at a high rate. Because otherwise you're just going to like, Antithesis is going to say, oh, we did your run and you have like 68 million exceptions. You might want to look at which ones are real.
Totally. You should definitely not take every single thing that, that you would find interesting in your observability system or whatever and turn it into a property, right? But I think taking the ones that would page you and turning them into properties is a great way to get people who have never thought about property-based testing to start thinking about what the properties of their system might be. I think the other thing that can help here is like a little bit of the Socratic method, right? Like a thing I found when talking to customers is often, if you ask somebody like, what are the properties of your system? They get this like deer in the headlights look and they're like, oh my God, get me out of here. And then if you say to them, hey, should your system always return an answer if 2 out of 3 replicas are up? They're like, yeah, totally. And if you're like, okay, cool. Like, do you expect that answer to come within some defined SLA? They're like, oh yeah, obviously. I'm like, okay, great. And it's like, okay, well, should the system, should 2 users ever be able to stomp on each other's data? Like, no, definitely not. Like, and so you can kind of tease it out of people. And I think that one thing that we're very interested in experimenting with is like, can we automate teasing it out of people a little bit more?
You need to clearly train an LLM to like have the dialogue with customers to figure out what their properties are.
Or to just look at their code and to guess at some properties and then present them to the user being like, hey, are these properties of your system? And by the way, even if the user says that they're not properties of their system, they're often pretty good guideposts in the state space exploration, because they're often the kinds of thing that some other developer at that company might have mistaken as a property of the system, which means that if you get it to happen, it might lead to a bug later on.
Do you want to present those semi-properties to the person who owns the system, or do you want to present it to Antithesis and see whether it follows it? And then I feel like you want to classify this, the properties that are seem to always be followed, and maybe those are properties. And then there's the ones that are not followed at all, and those you discard. And then there are the ones that are mostly followed, and maybe those are the interesting ones.
Yeah, this is not an original idea. This is an idea that the fuzzing people came up with relatively recently, but they did come up with it first. I think they call it speculative properties. I forget exactly what the term, it's in a paper somewhere. But basically the fuzzing spin on this is, I look at a function that I've executed 1 million times. And if I see that one of the parameters is positive every single time that function is executed, I just go ahead and add an assertion that that parameter will always be positive. Mm-hmm. And often, often that just is a property. And then even if it's not, right, it's very likely that if every time I execute it, the thing is positive, and then I get it to be negative one time, that's going to lead to some interesting behavior later in the system, possibly a bug because everybody else assumed it was always positive. And so the idea is we can both use it to guide exploration and use it as a kind of, preemptive property creation.
So I want to step back for a second. I think a meta thing I'm observing from this whole conversation is I wonder how you sell things to customers, right? I feel like this whole conversation is about what I think of as a really compelling and important kind of superpower that you can give software engineering teams. But we've already had a pretty long and complicated story to explain what's actually going on. Mm-hmm. To go to the perspective for a second of somebody running a business, how do you think about convincing people that this is a thing they should be excited about and want to pay for?
How do we sell to you?
So that's a good question, actually, right? How did we actually get to Antithesis? A little randomly, actually. So from our perspective, one of our engineers is someone who just followed the Foundation DB work and kind of knew about it and thought it was cool and was wondering what those people were doing. And at some point saw an Antithesis webpage go up and was like, oh, we have testing problems. Maybe this would be good, right? This was someone who's working on our kind of ultra low latency team that does a lot of very complicated multi-system, extremely subtle behavior kind of stuff, and was like, oh, it'd be nice to have deterministic testing for this. Maybe that would be good. And so we reached out and set up some conversations. I got to sit in on a couple of them. Not because we were oh, we need the old guy who's been here for a long time, but more because I'm nerdily really interested in testing stuff. So I thought it would be interesting. And then, one of our engineers, a guy named Doug Patty, who's actually previously been on the show, decided to try it out with Aria, which is one of our internally developed distributed systems that already has a ton of very careful work on the testing. Indeed, it's one of the places where we've done a lot of very careful work around deterministic simulation testing. Mm-hmm. And yet, we thought there was some actual real value add from Antithesis's version of this. And that's basically how we found you guys. But it's like a very like expert-oriented, people who are already in the tank kind of customer acquisition story. It's like the people who already built their own deterministic simulation framework are like, we'd like a better one.
Yeah, well,
we're not. I don't think we're a big audience.
No, we actually had a debate internally in the early days, which was, would people who are already doing fuzzing or PBT or deterministic simulation, would they be better customers, right? Because they are into this stuff, or would they be worse customers because they already have one and they're not going to pay a lot of money for another one? And it turned out that they're very conclusively better customers. But as you say, there's not that many of people like you. And so you're right, we do have to make it broader. There's a few arguments that we use, and then I think there's like a few trends that are really, really acting in our favor. And that are giving us actually considerable success in selling this to normal people. Not saying you're abnormal.
All good. I wouldn't object if you had.
Basically, the two main arguments, right, are like safety and speed, right? And you can think of those things as being on a frontier, right? For a given level of programming technology and skill and architecture and language choices and problem domain and whatever, there's some like efficient frontier between safety, like how sure you are that your program has no bugs, and speed, which is like how fast can you add new features and solve business problems. And I think of a tool like Antithesis as just pushing that frontier outward. And you can decide to reap the benefits in more safety, right? You can keep going at the same speed, but be really, really, really sure you don't have any bugs, which might be the right call if you're making pacemakers or like airplane guidance software or something like that. Or you can just keep the same level of quality, but do everything a lot faster because you're not writing as many tests, because when you do hit bugs, you're hitting them in your tests rather than in production. You're not doing some really long, slow, boring triage process with a badly written bug report from a customer while you're not sleeping and so on, right? So you can just go faster with the same level of quality, or you can kind of get a little bit of both. And, I think we sort of have all three kinds of customers, I would say, and they're all getting some real benefit from it somewhere on that frontier. I think the trend there's sort of two trends that have helped us a lot. One is just that all kinds of software is now either responsible for very, very critical stuff that needs to keep working, or responsible for making lots and lots of money and needs to keep working and keep getting better at making money. And so, a lot more people care relative to 10 or 20 years ago that their software works correctly and that they're able to continue to develop it quickly.
There are more critical systems.
That's right. The other trend that I think has been really good for us is like AI code generation, which hugely increases the salience of all these issues. And, I think moreover just has like made everybody realize the like Amdahl's law nature of being able to verify that your software works correctly, like being a critical limiting factor in how much software you can write. And I believe this was always true, right? And it just like wasn't obvious enough to people. But now it's like really, really, really obvious to people, right? I can have 10 Claude codes all writing code and it doesn't matter. I'm not going to go any faster if I can't merge those PRs after reviewing them and actually deciding they work.
Right. And like the two paths towards this is, one is figure out ways of making your software less critical, right? And if you can find a domain where you can like do a lot of stuff where you can get value out of it, but correctness isn't incredibly important, you can move at lightning speed, and that's great. And there's all sorts of cases where this is true. Like if I am like a software developer who wants an analysis tool to understand what's going on in my program, it's like, it doesn't have to be all that right. It can like help me some of the time and not succeed other time, and it's kind of fine. It's kind of a throwaway tool that I just make and use. And like that's super great. And you can just like vibe code that and it's awesome.
And by the way, I think there will be many successful companies built to make it easier to have that kind of software. Things like zero trust hosting, things like very powerful security guarantees around a piece of software so it can't do any damage, things.
Security guarantees, and I think also just like picking the right abstraction boundaries.
Yes.
Figuring out, if I want to make this whole thing useful, what pieces have to be reliable and what pieces don't have to be reliable. So it's like there's a whole new kind of software engineering challenge of how do you build these architectures that let you leverage less reliable code. So that's like one direction to go. And the other direction is just getting much better at verifying.
That's right. That's right. And right now, I think that has suddenly become interesting. It's very hot all of a sudden, which is kind of fun because, this was like a backwater, in some ways a deliberately chosen backwater for a long time. And now there's all this interest.
Wait, what do you mean by a deliberately chosen backwater?
Oh, if you are like, sure. So basically, if you're trying to decide what to make a career in, right? I talked before about how, there's a lot of careers where you're not going to have world-class success unless you are at an extreme of the distribution of people.
Like being a violinist or a mathematician.
Correct. One good way to be at the extreme of the distribution is to pick something where nobody else who is very talented is interested in it. And then it just is actually much, much, much easier. And you have to, you can't pick like, making paper airplanes or whatever, right? Like nobody super talented is interested in that because there's not a ton of economic benefit in that, not a lot of benefit to the world in that. But if you can find a sweet spot where something is like both really, really, really important, but for some reason, nobody else has noticed it's really, really, really important, or people know it, but they don't want to do it anyway.
Because it's painful.
Because it's painful, or because it sucks, or because it's low status, right? Like that's actually an incredible arbitrage opportunity. And so that was actually a lot of why I got interested in testing. This is like janitorial work. All developers hate it. Like, the number of smart people who have thought about software testing is very low because...
Although I have to say, so when I started at Jane Street, I was super incompetent. What did I have? I had a PhD in computer science, which is doesn't tell you how to be a software engineer. And I was not super good at it. And I didn't know anything about testing. But just over time, over the many years of thinking about these systems and building them, I've come to realize that not just testing is important, but it's super interesting and fun.
It is.
When you do it well, right? There's a lot of engineering work that it's one of these things that if you don't do the work to build good systems for it, it's horrible and nobody likes to do it. And there are lots of companies that solve this problem by hiring a whole different tier of people to be the testers because it's so low status that you can't get the real software engineers to do it. So you get other classes of people to do it and you just make it a different class job and it seems like a terrible way to run a business.
Yeah, I actually believe that the world is fractally full of things that are incredibly interesting and incredibly ignored by the entire world. I believe that there is tremendous low-hanging fruit here. It's not just software testing. Things that are super economically valuable, super interesting, and that nobody is doing. The key, though, is even if you find such a thing, your problems have not ended because now you need to convince other people that it is actually super exciting and cool, which you might be able to do kind of one-on-one. But if you want to start a successful company, you need to somehow make yourself legible to capital in the words of somebody who I like. So, that's a whole nother challenge. We got a little bit lucky there, right? As soon as, as our company was growing and scaling, we'd kind of laid all the groundwork and the foundations here. And then suddenly this giant thing happened in the world that made what we were doing super legible to capital. And, that was just a nice stroke of luck. I think we would have succeeded anyway, but it's always nice when things break in your favor.
Right. So what you should ideally do is pick a neglected area of the world, operate in stealth for a while, get a head start, and then cause the area to suddenly not be neglected.
That's right. That's
but only after you have done a lot of pre-work.
That's right. That's what we somehow managed to do.
Actually, the capital thing is a thing that may be a good thing to talk about for a second. So one thing that we got involved with, so we started using Antithesis as a product and we're excited about the actual results. I guess a thing I didn't say before, which was one thing that made us really happy about it, is it actually found bugs that we didn't find before. It allowed us to do more aggressive, larger scale kinds of simulations, even though we already had a deterministic simulation.
And your systems were really well tested.
Right. Really well tested and had a really good record of a low number of bugs in production. But the curse of a system that has a really good record of very few bugs in production is people start relying on it, having a very good record of very few bugs in production in the future. Mm-hmm. And so the stakes go higher and you end up using it for more and you want to put more engineering into making it yet more reliable.
That's a super interesting testing problem in its own right, by the way. If your system performs better than its SLA, everybody who depends on you will start to assume in code and otherwise that it will always perform better than SLA. And then if you ever merely meet your SLA, everything will go down and crash.
Yeah, that's basically right. I've often wondered what are SLAs for. I have not found like the whole like form of an SLA to be a particularly useful like engineering mechanism like in practice.
We at Foundation DB, we actually invented a technique. We invented it, but others have invented it too. But we call the technique bugification. And the basic idea is if you have a piece of code that you have written well, such that it 99.99% of the time does way better than its promise, right? Like, it returns an optional value, but it always returns a value. You should, when running in test, sometimes just make it do the pathological thing with some low but real probability so that anything that depends on that code, all the callers get used to the fact that it can like exercise its full spectrum of behavior.
Right, and I guess famously Netflix was like, actually, we'll do this in production.
Mm-hmm. Yeah,
right? That's the whole chaos monkey idea.
I'm not such a fan of that.
Yeah, there've been spots where we've used it. I have complicated feelings about it. I do feel like it degrades the quality of your overall service in a way that is often just economically inefficient and you just don't want.
I think Amazon actually might offer an entire region where like you deploy your code there and their services will all
the bad region.
They'll just like return 500s sometimes, whenever, yeah. It's actually a pretty good idea.
Yeah, certainly seems good as like a mode of testing.
Yeah. Sorry, you were saying I interrupted
you. Yeah. So I guess we were talking about capital. So we got involved as customers. We found it like useful for finding real bugs. We found that it again, like in the way that you might expect, increased the ambition of the kinds of things that we would try to do, right? There are like things that we are willing to experiment with that are riskier, but we feel like more of that risk is tamped down by the better testing story. So it's been like a very positive experience for the places that we've applied it. And then we got involved actually in leading Antithesis Series A.
That was pretty
which
cool.
Was like, yeah, which I think you guys found to be a little bit of an interesting and weird experience, and we found to be a kind of novel experience too. And I'm kind of curious how it felt from your perspective.
Yeah, well, you guys haven't invested in very many companies, so it was not a thing that we thought was even on the table or likely to happen. I think it basically happened as like a happy coincidence. You heard through the grapevine that we were raising money. And then I think one of your corp dev people came and chatted with us, and we were initially like, oh yeah, whatever. Like they want to do some small strategic investment. And then I think he was like, we would consider leading the round. We were like, what? Like that's completely unheard of. But it was actually an incredible experience. Silicon Valley VCs are great, and they have many forms of knowledge, and they have they have deep networks, and they have deep experience from working with many, many companies that lets them give you all kinds of good advice. But they are generally not super active users of your product. And
certainly not of this product.
It's certainly not of this product. That's right. Maybe Carta had an easier time with that. And so I think one of the amazingly cool things about having Jane Street as an investor is just that I feel so very aligned in terms of you understand our vision and what we want to do. You guys give us constant good ideas about the product and strategic perspective on the world informed by your use of it as a customer. It's a very different kind of advice than most investors can give. And we've already got the Silicon Valley VCs, right? We have that. And so having you guys as well just feels like an incredible superpower.
Yeah, and I do think this lines up. I mean, we are not certainly not primarily and not majorly like a VC. That's not the primary thing we do. But we have been doing more and more investments over the years, and those investments have mostly been in the form of companies where we are connected to the underlying work, where we care about it, our customers or want to be customers of it, and we feel like we have direct kind of subject matter expertise on the area in question, and that we really believe in the product and think it's great and want to use it ourselves. And I think that's the kind of thing where we think we actually have some meaningful leverage.
Yeah, and I think you guys have done quite well. I think, you're not VCs, but I think you've done a pretty good job of spotting opportunities. And I think you've got a track record of spotting them sort of before they become quote unquote legible to capital. I think you guys were very early in Anthropic, if I don't misremember. And I think you guys invested in Anthropic at a time when they actually had trouble raising money, hard as that might be to believe, because you saw something that others didn't, and I think with us, right, like you invested in, 3 months is like a very long time in tech these days. Like, I think, today, every single investor is probably lining up to invest in testing companies because it feels so salient, with AI code gen. But like 3 months ago, when you guys made this investment, no investor had ever heard of software testing or cared, like, to a first approximation. And, I talked to a lot of people who were like, nobody has ever made a software testing company that has made any money. Like, why do you think you'll be any different? And who like really needed to hear arguments, right? Whereas I think you guys sort of spotted that opportunity before the professionals did.
And it's worth saying, I think we were interested in and excited about Antithesis and the value it provided independent of the AI angle, right? I think the AI angle added a lot more, but I think to some degree, I think we share some of your basic intuition that this stuff has always been important. But it definitely, as a kind of, market hypothesis, makes a lot more sense in the present world where this stuff is becoming more salient because of the challenge of verifying AI generated code. I'm actually curious how you think about the product really working in this context, because in some ways I think it's a really good fit. And in some ways it's not quite perfect, right? Because one of the critical things that you want, both when you're thinking about RL, right? You want to like provide feedback to agents as you are training them. And then also when you actually try and use this stuff is you want reliable feedback on whether the thing that they did is good, but you also want fast feedback. And Antithesis is good at a lot of things, but it's not like super fast, right? When you kick off an Antithesis run to find your bugs, you might come back tomorrow to look at the results.
So I actually think that I do think that there are ways it doesn't fit well, but I think that last thing you said is a unfortunate current limitation that is like highly contingent and will not be for long. Basically, Antithesis began, like its bread and butter was like very, very large distributed systems. And those very large distributed systems tend to just kind of be expensive to run, period. And so there was not tremendous like pressure on us to make all of the constant factors of running our software like really zippy and snappy. And, basically people who were testing this stuff were just okay with getting a relatively slow answer. And so we weren't under a lot of pressure to do otherwise. As we move beyond distributed systems, which we are doing this year, that equation changes. And I think you are going to see that Antithesis gets way faster at giving results. And we have a lot of really, really cool projects underway that are going to enable that and make that possible. And by the way, I think that even for distributed systems, you might be able to start getting pretty fast results. Like, I don't think there's a law of the universe which says you can't test a distributed system fast. At FoundationDB, we often got good quality answers within minutes or tens of minutes. Very thorough answers. Sometimes we'd even find the first bug in less than a minute. And I think that is totally a thing that you will be getting from Antithesis, in the next year or so.
So what are ways in which, beyond the kind of timescale issues, what are ways in which you think maybe it doesn't solve all the problems for
for AI in particular?
Yeah.
Yeah. Well, so, okay, there's a few things. Let's talk first about what I consider the most fundamental one, and I think the most interesting one. And I don't think that this is like catastrophic, but I think it's like an interesting challenge that everybody who's doing any kind of autonomous software verification, whether that's property-based testing or formal methods or code review or whatever, is, in my opinion, not thinking about. Okay, so code generation tools, code synthesis tools, specification-driven tools like that have existed since way before ChatGPT existed, right? These have existed for 20, 30 years, and nobody ever used them because they suck.
Yep.
And why did they suck? Basically because they all acted like evil genies. You would say exactly what you wanted the program to do, and the non-LLM program synthesis machine would crank out a program that exactly matched your specification and totally did not do what you wanted to do.
Yep.
Right? You've had experience with this.
Yeah, I mean, I've been sort of paying attention to like the program synthesis literature for a long time. And like there's a lot of really great research and a lot of great researchers doing interesting stuff, but remarkably little practical applications in it. And all the things that people work on end up looking mostly like toys. Like I think maybe like the single most successful like program synthesis style thing is like Microsoft Flash Fill in Excel, which is like, pretty good. But like, I feel like for all the like smart work that's gone into this stuff, you would expect like in some ways to have more practical impact. But like the problem is just really hard to do well. And I think in some ways, one of the reasons why LLMs are better than classic program synthesis is that they are less evil genies.
Yes.
And like, they're not really specification driven. They're like vibes driven. Like you say some stuff and it makes some inferences and there's a lot of like leaning on the priors of the thing it's seen in the past and what it generates. And it's just optimizing less.
Exactly.
Right.
Exactly.
And so, of course, the RL process makes it optimize more, right? So this whole thing where you have basically like eval hacking, where it like does kind of whatever it can do to try and get like the light to turn green. Right? This is a problem with like LLMs. It's a problem with people, right? Sometimes like you have some system where you have some checks in place. And like, I think we talk about internally is like, don't just play the video game, right? You don't just try and like score. You want to actually like do the right thing and use the alerting as a way of understanding what's going wrong. But if you turn the alerting into the thing that you're actually optimizing for, very bad stuff happens.
Goodhart's law. Yeah.
Yes.
Yeah. So that's exactly right. Basically the reason I personally thought that AI code generation wouldn't go anywhere like a year or two ago because of exactly this. I had experience with program synthesis tools. I was like, oh, they're all evil genies. They suck. I think a lot of people who had experience with these tools had the same kind of reaction. And what we all missed was exactly the thing you just said. LLMs are not like, they actually want to make you happy, right? Like they
for good and ill.
Right, exactly. They're like the sycophancy thing is like, there's actually a nice flip side to it. Like they've been trained on like zillions and zillions of examples of people on Reddit and Stack Overflow being helpful. And then they've been RLHF'd by people who reward it for being helpful. And so it actually is kind of trying to write the code that you're asking for, as opposed to like write code that fits the specification that you asked for in the least amount of work or whatever. And what happens when you put these things in a loop with something that's like, no, try again, no, try, right? Like it kind of shifts it back into being an evil genie a little bit.
That's right. Although to be clear, I think that the people who are doing the training are no fools. And you've talked to some people who do this kind of training work and they pull the system simultaneously in multiple directions, right? There are things that you do to pull it in the direction of trying to just satisfy the immediate feedback goal and also trying to pull it in the direction of like fitting more the general distribution and not just kind of totally getting completely twisted out.
Yes, but the problem is that when you're done training, when you're actually running this thing, if you run it in a loop, it's still pushing it back towards being an evil genie. Not in terms of like shifting its weights and so on, but just in terms of its behavior and what it tries next. Like I've seen this happen even with just very, very, very not sophisticated, like not property-based testing, right? Like I have Claude Code and I'm like, hey, do this thing for me and make sure the tests all pass. And like, if the thing is hard and it can't do it correctly, eventually it deletes the tests. Yep. Or eventually it like makes the test pass in some trivial way or in some way that is totally not what I want. Yeah.
And I do think this is getting a little better, but the phenomenon is still very strong.
Yes. And I basically think that the more powerful and unyielding the validation step is, probably the worse this overall effect gets.
Yeah. And another, I think, general problem with these issues, we talked before about the kind of functional properties of the software that you're optimizing for, and then the non-functional properties, like all these kind of architectural and clarity and extensibility properties.
And those probably get worse. Yeah.
Right. Because if you look at the agents, their efficacy depends a lot on those non-functional properties. They just do better in contexts where things are tighter and more extensible and easier to understand and where the systems are fundamentally simpler, but they're super bad at maintaining those properties. I feel like the thing that Anthropic came out with of like the C compiler that they built was a really interesting example where they got really far. They built like a pretty good compiler. I mean, not actually a good compiler. You wouldn't want to use it for anything, but like it was an impressive technical feat. It's a little bit like the talking dog. It's, it's not that what it says is so great, it's that it talks at all. Like that they got a compiler that got to that level is impressive. But the thing, a lot of people have focused on like, it didn't do any type checking and it didn't do this and it didn't do that. And that's like a little interesting. But the thing I was more struck by was the way in which it ended. And they were unable to make future progress, to make more progress with this like team of agents approach, because it just started to be the case that as the agents started to make improvements, they would break other stuff at such a rate that they couldn't actually net.
Which is an experience that every junior engineer has had too, right? And it's why things like architecture matter, and it's why things like, making your system like actually fit together in a minimal and clean way and have concerns be orthogonal and well factored and all that stuff.
Yeah, it's just like a bringing to life the like deconstruction of the non-functional properties of your software.
Right.
And I think that's one of the reasons why, it seems to me like testing, while still important, just isn't enough, right? You still need to think about architecture. You still need to think about the cleanliness of the code and all of that. Like,
that's
it's not,
right.
I think it's you just have to maintain those non-functional properties.
And it's possible that if you put an LLM or an agent swarm or something in a loop with a really strong test or a really strong formal verification system or something, it's just going to make the architecture worse and worse in order to get the test to pass. Like, that seems like a very plausible failure mode.
Yep. So how do you think about kind of the completeness of antithesis as an approach, right? Like, to what degree are you like an antithesis maximalist? I mean, I don't so much mean antithesis the product, but the approach, right? The approach is like, we're going to have a kind of ability to do these high-powered, end-to-end randomized tests of our systems in a way that like are very cross-cutting and can check lots of different properties. That's not the only way to write tests, right? There's like the classic, I'm going to like at a small scale write a unit test, which like sticks an example in there and see whether the example behaves in the way that I want. Like, to what degree do you think the antithesis approach is really the approach that people should be doubling down on? And to what degree do you think, we should be throwing many things at the wall?
Yep. So I will first say that I want to dispute the idea that there's an antithesis approach.
Okay.
So the thing that we've told people, including all of our investors from the start, is that this is not a solutions-based company. It's a problems-based company. Like, our goal is to make software validation incredibly cheap and easy and like running water, and find all the bugs in all the software by any means necessary. And it just so happens that we thought that the lowest hanging fruit, the best way to like start making money and really start making a dent, was to do this deterministic simulation thing and to make that cheap and easy for people to adopt. But, that is not the full extent of our ambitions. If we someday, I kind of dream of a day where software engineers don't need to know what deterministic simulation or unit testing or formal methods or, concolic solving or any of these things are. They just hand their software to a box and get back like it worked or it didn't. And obviously there's going to have to be a lot of very complicated things that happen in order to enable that vision. But like, that's the dream. Okay. That said, there's a reason we started where we did. And it's that I think we do believe that this technique is uniquely high leverage and a little bit uniquely low adopted for how high leverage it is. And, I have seen both situations. Okay. So like, our team, right, is always dogfooding our own product, which is a thing that every team that's making a developer tool should do, or really any kind of tool.
It can be harder if it's not a tool that you use, right? Developer tools are where it's easiest.
Yes. And so we that's both fun. I feel like that both shows the power and the limitations of the current basket of tools that we offer to our customers. Like, we have gotten ridiculously far with just doing antithesis style deterministic PBT on everything that we write, including like UI components, browser-based stuff, including like very low-level things, just like everything. we have entire extremely complex systems that are literally only tested with antithesis and nothing else, where like nobody has written a unit test, and we're like one of the policies of that area of the code base is that people don't write unit tests. You just add more, more sophistication to the property-based tests to cover whatever you need to cover. And then there's some parts of our code where I'm like, man, there should just be a unit test here, and then that would make this a lot more straightforward. And so I feel like this is like kind of a wimpy answer to your question, but I kind of feel like there is a line, right? There is a place at which you should just write the stupid unit test, or you should not use testing at all. You should be using something like proof-based techniques because of the nature of your problem domain, or you should be using exhaustive testing, right? Like if your function takes an int 32, you can just try all of them.
Yep.
Won't take that long.
Definitely done that.
So like, I think that line does exist. I think it is a lot farther away than most people realize. Like I think more things are amenable to property-based testing than people think, and that if we can make it easier and more powerful, people will use it in more situations where they don't currently use it.
Yeah, I think that's right. I think your point about it being neglected essentially feels right to me as well. Of like, if you're going to see where you can add a new thing and make a big change, I feel like that's a natural thing to work on. I do think the other kind of testing is like really important. I think there's a kind of like unreasonable effectiveness of example-based testing, right? Like I think it's in some ways, it's almost kind of sounds like a comically bad idea of like, I'm going to have a big complicated program and then I'm going to test it by like writing 6 examples. But like to a surprising degree for like modest complexity things, it actually like works super well. Mm-hmm. And I think works especially well in code bases that have other good non-functional properties. Like a thing I've long been struck by is the degree to which having a really good and expressive type system that like captures a lot of useful properties of your program and tests together, there's a kind of multiplicative effect where it has this very strong property to kind of snap in place. Like you just kind of put your finger on a couple of spots and make sure that the behavior is what you expect it is. And like the kind of analytic continuation of your program, the rest of the behavior is kind of smooth enough that there's kind of like only one natural thing for it to do. And it kind of just like clicks in and does that one thing.
Yes. I think a thing I've said before is like, there's this funny thing about impossibility results where they often are actually cluing you into like a thing that you should really try and do. And the reason is that a lot of impossibility results, this is true in mathematics, true in computer science, true everywhere, kind of rely on this like anti-inductive property, right? It's like I'm going to prove that the thing that you're trying to do is impossible by constructing a really fiendishly awful example and like, your technique fails here. And I'm going to adapt it based on the technique that you're bringing, right? And like, that's kind of how, impossibility results in mathematics often work, like diagonalization arguments. It's also true in many famous impossibility results in computer science. And I think what's significant about this is like, we're not trying to find bugs in every random Turing machine, or even in a random Turing machine drawn from the space of all Turing machines, right? We're trying to find bugs in software that people write to accomplish business purposes. And that is a very, very, very infinitesimally small subset in the space of all possible programs. And it's like a really nice one, right? It's like, it's like smooth functions or functions that are everywhere differentiable or something. It's like, these are programs that people have built for a reason and have built so that they can like come back and modify them and extend them someday. And I think it just turns out that in that space of programs, testing is actually way more tractable than it would be in a completely random program.
Yeah, there are tons of things like this. Another fun example from our world is type checking in OCaml and any language in that ecosystem or in that kind of rough space of languages is like doubly exponential. Mm-hmm. Like you can write, an 18-line program that will not finish type checking until the heat death of the universe. But nobody does.
Nobody does.
It turns out those programs don't make any sense.
Right.
And you can find that, like, if you think really hard, you can figure out what those programs are, but they're not actually a practical part of the actual things that you run into when you actually do the real work. And again, I think this behavior of like real world programs being a much smoother, tamer, better behaved subspace is a really important one for lots of engineering questions.
It's true. Although we do trollishly inside of our company have the inside joke. Like at our last company, we violated the CAP theorem, and at this one, we're violating the Turing-Halting theorem. So you were just moving up the hierarchy of theorems.
Yeah, what's next? What's the next theorem you need to violate?
I don't know. That's a good question.
It's a good company formation question.
Yeah.
So we've talked a bunch about the kind of engineering practices you're trying to create in the outside. And a little bit on your engineering practices internally. But I'd like to hear a little bit more about that. How does Antithesis operate internally? Mm-hmm. And I'm kind of curious how that differs from what you guys see in the outside.
Sure. So I think I learned a useful trick from somebody recently, which is when you're talking about your company's culture, culture is always a set of trade-offs. Right? There's no purely good cultural attribute.
Yep.
They're all just choices on a spectrum, and being one thing implies that you're not the good things about the opposite. And so I'm going to try and phrase this in the most edgy way possible, maybe. So I think that we generally believe a couple important premises that have led us to pick a pretty weird by outside standards place on a lot of these culture spectrums. I think we believe that for many kinds of projects, the overall cost of the project is dominated by the number of mistakes you make. Like big architectural mistakes early on in a project can just have an exponential effect on the amount of work that it takes to get the project done. I think we also believe that one of the biggest scalability barriers to human organizations is communication, and that one of the things that is worst for communication is lack of trust. And yeah, let's just start there. So given that you believe these things about the world, what would you want your engineering culture to look like? Well, basically, we try really, really, really hard to talk a lot about what we're going to do before we do it, and to debate multiple possibilities for how we could accomplish some important objective before we go all in on one. And that doesn't mean that we don't prototype. Often these discussions do involve people bringing prototypes and showing them to each other and debating the merits of them. But it is basically considered uncouth at Antithesis to be we're going to do it this way, and to not come with two alternatives and then explain why you picked this one over that other one, and then explain why you don't think there's a great third alternative, right? And that I think drives some people completely insane. There's a lot of people who are just man, I want to put on my headphones, I want to write my code, leave me alone. And they just won't have a great time at Antithesis, where people are going to walk by and be and they're, we all work in a big open room, exactly like you guys do here. And people will just come look at your screen and be hey, why are you doing that? Which is not a thing that would happen at some other companies I've worked at. So we're highly collaborative, highly deliberative. Collaborative does mean that we're all in a physical office together for the most part, because it's, adding any friction to communication just means that you get a whole lot less of it.
Sure.
It means that we don't really care about hierarchy very much. There is hierarchy. Every human society and organization has hierarchy.
I've heard you're the CEO.
That's right. But everybody's opinions can be questioned and debated. And just because somebody is the big boss of some particular part of our software architecture does not mean that they get to sort of be dictatorial or rule by fiat. People can just come and be I think you're making a stupid decision. And that's a very normal thing. And we try to praise people for sticking their necks out and making statements like that.
Yeah, a lot of this feels very familiar. I think we've taken it a pretty similar role. It's not the whole big tech thing of you're an L8, sergeant, second class, something thing. It's just we just don't think makes a lot of sense for us. And,
yes.
People have functional titles as someone who's responsible for a given area or whatever. But there's no kind of general notion of title that shows up somewhere.
We're the same way. And we're actually debating whether we need to change this at some point. But basically, every single person on our engineering team has the same title on their job offer. It's senior engineer.
Yeah, for a while, I think for weird legal reasons, we thought we needed like two different ones. And like for the first 2 years, you were a software engineer, and then afterwards you were, but like with no internal like referent or anyone paying attention to that kind of stuff.
Yeah. So the thing, which I should probably not be saying, but it's true, is we sort of treat titles as like as tools, right? Like, so when we're interacting with the outside world, people can adopt any title they wish, pretty much. So it's like if somebody really needs to get into a conference, like suddenly they're a senior staff engineer, third class or whatever. Like whatever our marketing people decided would be the correct title for you to get into that conference. And, people, can use sort of whatever titles in their bylines that they think would be most useful or put on LinkedIn. Like this is like a form of compensation. Like, please pick your title. But internally, there are no titles.
Right. And I think part of that is we very much want a culture where the thing that matters is the idea and like what's the actual thing you're trying to do, and not like the particular position and rank. And like no culture is perfect. Our culture is certainly far from perfect. And I don't think this ideal 100% works out in all the cases. But I think it's definitely like directionally much more this way here than I think in lots of other places. And I think it's a little disorienting actually sometimes for a strong experienced person who comes from somewhere else and lands at Jane Street. It's like, doesn't have like a rank that helps them navigate. And we have to actually be much more intentional about like trying to get them into the right spot and make sure that like people quickly realize that like, oh, this actually is a person who's like substantively worth including in and listening to in a bunch of different contexts. Because we like sort of just don't have the title tool as a way of making that happen. So you have to use other methods to get people in the right spot.
So how do you guys think about maintaining that as you grow? Because I think like this kind of organization is really, really effective and also really hard to preserve if you grow quickly.
Right. So I think one of the things is, even though it feels kind of quick, we just kind of haven't grown quickly. We've been relatively disciplined about growing at, I don't know, what feels like a fast pace between 10 and 30%, depending on the year, usually south of 30. And when we've been on the upper range of that, we're like, wow, this is like really uncomfortable. Like we kind of maybe want to slow down a little bit. And we really feel like it's important to be able to take the time to absorb people into the organization. I don't know how to run a company where you need to double every year for a few years. It seems terrifying.
Yep.
And it's just not how we've operated. So that's one thing. We've also just been very rigorous about interviewing. I'm just trying to make sure we're bringing in people who are very good technically, like that's really important, but also who fit in culturally, who are like nice and humble and have good second order knowledge and aren't made super uncomfortable about being wrong. Because like we're all wrong a lot. Like you make a lot of mistakes and you want people who are comfortable owning up to those mistakes. And
we actually deliberately design our interview to try and assess these qualities. That's like a significant part of why it's set up the way it is.
Yep. Yeah, no, we have the similar things from our side. Like we think it's after some early mistakes based on not understanding this, we realize that like you really don't just want to solve the people who are like best at solving the puzzles. Like being good at solving puzzles is really good, right? Being just like having like, high wattage and just being really smart at stuff is good. But you really want to make sure that whoever you're interviewing, you see how they operate under challenge.
Yep.
Because like you're going to take everyone and, there's more they can do, and you're going to keep on asking them to do more until the job is hard. And there's no end of hard problems to solve. And so you want to see how people operate in that context.
The thing you mentioned of like niceness and being good to work with and so on, that I think we fully agree with that. And that comes from another sort of like fundamental observation about the world, which is most problems are hard enough that one person alone cannot solve them. And even if they were, like your individual value that you bring just by like the stuff that you do in almost every case is dwarfed by the positive and negative externalities that you cause on the team. Like, you are going to be chatting with your friend or your colleague at lunch and like have some good idea that makes their job easier. Or you're going to be mentoring some junior engineer and teaching them some trick that's going to make them more valuable for the rest of their career. Or, conversely, you're going to be like being really mean to somebody and then they're in a bad mood for the rest of the day and aren't as productive, and also just make the place like a less fun place to work. And so like that stuff just kind of dominates actually when you get to a sufficiently large organization size. And it's not to say that you can be ineffectual and really nice and have a job. Like,
Right.
you
do have to get things done.
There is still a bar. That's right. Not least because having people around like that is terrible for morale.
That's right. Lowers the intellectual density.
That's exactly right. But it's sort of like you just need both. And we're just not going to accept you unless you are both really great on your own and also really great and magnify the abilities of the people around you.
Yep. Yeah, I think that's totally true. One point about the externalities really matter. I think that's true. I feel like you could take that kind of thinking in the direction of thinking that what really matters is organizational stuff and how things are put together and teams and all that. And I think that stuff is all really important. I also feel like the shape of this business makes very clear to us how amazingly valuable strong individual contributors are. And a lot of that value is the externalities that they have, but individuals in both a kind of trading and a technology and in various other contexts who are just super good at their job and not kind of built to be large scale leaders can still be just enormously valuable and enormously well paid because that kind of individual contribution can just move the needle in a huge way. So
yes.
It's both this kind of collective stuff it really matters, but also people's just individual power to do amazing things is super important and is really important to recognize and compensate people for that kind of stuff.
Yeah, I totally agree. I think, another thing that helps with keeping that kind of environment as you grow is just having strong esprit de corps and a strong sense of yourself as an organization. And I think, quirky cultural choices and quirky technology choices actually help with that. I think it makes people hold their heads a little bit higher. It's yeah, I work at Jane Street. I work at Antithesis. It's a slightly weird place. People who don't work here definitely don't work here. It's not just another interchangeable company. And I think that actually makes all these cultural problems a little bit easier to solve on every dimension.
Yeah, certainly I like to think so, since I think I'm deeply culpable for our weird choice of programming language. So I hope that has some positive externalities.
There's actually a really interesting paper I read recently that talks about this in the context of Hasidic Jewish merchants in the New York Diamond District. So
amazing.
Are you familiar with this? The researcher named Barrick Richman?
I am familiar with the stores. I have seen those guys and been in this, but I have not heard about the research.
So they have incredibly low transaction costs with each other. They lend on credit. They they don't require huge amounts of collateral. They don't sue each other. They are very, very, very low transaction cost. And that is a big part of why they're so successful. And Richman studies them and basically concludes that a lot of why they have such low transaction costs is because they are clearly not the world, right? They're clearly an insular group of people who all know each other, who all trust each other. And, and where leaving that group or joining that group is very expensive. And he basically thinks that kind of makes all of their economic dealings more efficient and smoother. And it's actually a super interesting paper.
Yeah, that's interesting. I do think the high trust thing matters a lot for us. I do think it reduces the kind of internal transaction costs. It's kind of easier to get things done. A thing that I'm kind of always worried about, but still delighted seems to be still in place, is that the place, it's still a place that can pivot quickly. When something different needs to happen, you realize there's a new emergence and we have to change things and move people around and focus less on this and more on that. We're able to do it in a way that feels generally pretty positive. People who come from other organizations are sometimes we say, oh, we're reorganizing this area, and people are there's a reorg, and they stiffen up in their chair, and it's what are you worried? What's wrong about we reorganize stuff all the time. We change where the seats are. We move. It's all happens kind of routinely. And I realize, then I hear stories about what reorgs are like at various big tech firms. I'm oh, now I see what you're scared of.
We've made two huge pivots in the last 2 years that I'm actually just tremendously proud of our team for doing, because they both required astonishing levels of intellectual humility and dealing with reality, which is the thing that organizations are usually pretty bad at. The first was basically, we had been in stealth mode doing R&D, deep research for 5 years. And then we came out and started selling it. And at some point, we kind of realized that we were still thinking of the world in a very R&D way. And then in particular, we just were not listening to our customers and did not have the customer service mindset at all. and we're really, really bad at listening to their feedback, and we're really, really bad at like doing what our customers wanted, and that maybe this is like not a great property for a company trying to have more customers to have.
Yeah, that makes sense.
And so like it's like kind of like sense dawned on us, and eventually we were just like, oh, we have to change how we think about everything and how we do everything. And the company just like all pulled together, and we're like, okay, we're going to be different now. And we did, and we like turned on a dime, and I think it went really well. And it's like not 100% done, but it's like notably and distinctly different. And the second one was AI, where basically for like most of the last few years, we were kind of like, AI coding is dumb. It like doesn't work. It's like not like mostly a waste of time. Like you shouldn't do that. And then like, Opus 4.5 came out, and everybody played with it at home, and we were like, oh crap, this actually works now. And it was just like, again, this like a lot of places, I think, would have trouble admitting that they had been that wrong about something that important. And instead, the technical leaders at our company, who I respect tremendously, not least for this, were sort of like, okay, we were wrong. Like let's deal with the world now. Time to change, and like very quickly everything got reoriented and recalibrated. And like I think that's what it looks like for an organization to be able to like adapt to a changing environment.
I do, by the way, think that was like, in some sense, the right pivot point. I kind of feel like we've actually been spending an enormous amount of energy building tools and trying to get agentic coding working effectively for a few years now. And I think up until now, it's kind of been bad. Like there are a bunch of things for which it's great. But like for the majority of work you're doing like critical software, I think had been more likely to slow you down than speed you up. And it had this feeling of like, spending a bunch of time building a boat and having a sail there and like holding the sail up and like there's no wind coming. We get some utility out of it. People use it for some things. The tools get better. But like with the recent round of models, both from like all the vendors actually at this point, like the models are much better.
Yep.
And suddenly it feels like there's wind in the sails.
Yep.
And
Yep.
now it feels like we're pretty well prepared and have, a good team in place and are like, being able to deliver a lot of value based on this stuff. But there was an awkward period of like, these things are miraculous, but also not super useful. And now they seem both miraculous and useful.
Yep. Yeah. So I don't know. It is, I think also like on all of this cultural stuff, one of the most important things is just having senior people modeling good behavior. Like we all take great pains. The senior people of the company take great pains to like give credit to others, right? To like, to loudly proclaim when they were wrong or did something dumb. Just like showing that is what we do. Everybody is always looking at the implicit, like we all have the same title, but you're looking at the implicit leaders and seeing how they act. And so having them act the way that you want everybody to act is like kind of step one.
Yeah. And I just want to say like, don't give it up. Like it is possible to maintain at larger scale. I don't want to say we've done all of this perfectly, but it echoes a lot with the kind of things that you're talking about. I think we really have been able to keep up with it. By the way, one other thing that has been, I think, important is the place is designed for long tenures. Mm-hmm. Like we just have people who have been around here for a long time. Like the turnover rate is pretty low. And I think that affects a lot of things about the culture. It keeps a lot of institutional knowledge around and it helps maintain the culture. I think one of the things about cultures is they're kind of mysterious. You don't actually know which parts of it are the ones that are load bearing. And so you want to be very careful about preserving it in a somewhat conservative way. There's a lot of like Chesterton's fence kind of thinking going along.
That's why we're in DC. Everybody always asks me, why on earth did you put a ambitious deep tech company in DC and not the Bay Area? And it's basically 100% so that we can actually keep people and invest in them for the long term. It's not just that the Bay Area has tons and tons of competition. It's actually just that the Bay Area has a meta culture of job hopping every 9 months to get slightly more RSUs. And basically, once every company is in that equilibrium, nobody invests in anybody. And it's like very hard to be the one that stands out and doesn't act that way. Whereas in DC, people are used to working for the government and working there for like 30 years. And so the like kind of ambient expectation in the water is like, yeah, you're going to go work somewhere and work there for 30 years. And so we have ridiculously good tenure among our engineers and are able to invest in them. And it's just like a way nicer, in my opinion.
That's okay. That's amazing. Okay, that seems like a great note to end on. Thank you so much. This has been really fun.
This was awesome. Thank you so much for having me.
You'll find a complete transcript of the episode along with show notes and links at signalsandthreads.com.